Okay, I'm going to have us get back to section 3.5. We're talking about implicit differentiation. An implicit equation is just one that has not been solved for y. Okay, and when you want to differentiate an implicit equation, you differentiate x as usual, and then apply the chain rule to y. So we've looked at two examples so far. Here's another one. Find an equation of the tangent line to the graph of this equation here at the point 3, 1. 3, 1 would be a point on this graph if you were to check that by plugging in x equal 3 and y equal 1. Well, let's see. So I want to take the derivative of both sides. Now, constants can come out of derivatives, right? So I can bring the 3 and the 100 out there. And now I haven't taken the derivative yet. Okay, this is something I mentioned in the other video. Like I don't want to write dy dx. Okay, I only tack on a dy dx when I differentiate something in terms of y, and I'm finishing the chain rule in using that notation. So now I'm going to actually differentiate both sides here. Well, I'll leave the 3 as is. On the left, when you differentiate x squared plus y squared squared, that would be a chain rule. Okay, so I'm going to think of this as if it were just x squared. Okay, bring the power down to reduce the power by 1. You're leaving x squared plus y squared as is, but now you got to finish the chain rule, right? You got to multiply by the derivative of x squared plus y squared. The derivative of x squared is 2x, derivative of y squared is 2y, and then dy dx, since I just differentiated a term involving y, I want to make sure that I have that there, equals, okay, on the right, x times y, that's a product, so I need to use the product rule. Well, let's use that. So the first is x times the derivative of the second, derivative of y is dy dx, and then plus the second, is y, times the derivative of the first, derivative of x is 1. Okay, now I need to solve this for dy dx. I need to know a general formula that would give me the slope of the graph on this curve, and then I can figure out what the slope of the graph is at the point 3, 1, and then I'm on my way to getting this equation formed here. So let's solve for dy dx. You can distribute 6 into the first expression there, and then I'm going to FOIL this out on the next line. Also, I'm distributing 100 into these two terms on the right. Okay, so on the left side, I'm FOILing this out. 6x squared times 2x is 12x squared. The outer terms, we're looking at 6x squared times 2y dy dx. That'd be 12x squared y dy dx. And then plus the inner terms would be 12xy squared. And then the last terms, you're looking at 12y cubed dy dx. And we're keeping the right side as is. Okay, and how about anything involving a dy dx? Let's get that on the left. All the other terms, let's get that on the right. So I'll need to subtract 100x dy dx from both sides. I'm going to subtract 12x cubed from both sides and subtract 12xy squared from both sides. And so that gives me this next line then. Dy dx is in common to all three of these terms on the left. So you can factor that out of all three of the terms on the left. And then the leftover then would be 12x squared y plus 12y cubed minus 100x. You can divide both sides by that expression, and that way dy dx is all alone on the left. What we have here is going to simplify a bit further. Okay, if we so 4 will go into all these terms evenly. If you factor out a 4 from the top and a 4 from the denominator and cancel, then here's what I'm getting then in the simplified form. And make sure that you're simplifying, of course. I've mentioned that several times. Now, another thing to mention, so I had said this in the last video, the notation that you'll see in this section is going to be the Leibniz notation, dy dx, or y prime is used quite a bit in this section as well. You won't hardly see f prime of x notation. The reason is because a lot of the problems are going to be where you have an equation that is not a function of x. Okay, like this problem that we had looked at earlier is not a function of x, right? It fails the vertical line test. So I don't want to do anything with f of x up here. I don't have a function. I definitely don't want to do anything with f prime of x right here because I didn't have a function, right, to begin with. So be careful about that. All right. Now here's the graph of this curve that we had just worked with here. This fails the vertical line test. So I wouldn't want to use the f prime of x notation is the point. Use either y prime or dy dx. Now, we would like to know the slope of the graph at the point 3, 1. So I'm going to say at the point 3, 1, dy dx would be what? When you plug in x equal 3 and y equal 1. I've done that here. And simplify. So 25 minus 81, and then minus 9, that'd be negative 65 in the numerator. In the denominator, we're looking at 27 plus 3 is 30, minus 75 would be negative 45 in the denominator. Negative over negative is positive. 5 will go into both these numbers evenly. 5 times 13 is 65, 5 times 9 is 45. 13/9 would be the slope of the graph then at the point 3, 1. Now as far as the equation of the tangent line, I can now get that. So I'll use the point slope formula. Y minus y1 is 1 equals the slope, that's 13/9, times the quantity x minus x1 is 3. And get that into slope-intercept form. So when I distribute 13/9 into these two terms and then add 1, okay, I'll have y equal 13/9 x minus, it'd be 13/3, but then I'm adding 1. 1 is the same as 3 over 3. Negative 13 over 3 plus 3 over 3 would be minus 10 over 3 then. Okay, now they're not asking us to graph this curve, but I did that. We'd have a kind of like a figure 8 type curve, which we call a lemniscate. You guys will work with lemniscates a little bit in Calc 2, not a lot, but it's in one of the chapters. Okay, and anyway, I plot the point 3, 1, and I've drawn the tangent line. And I think I mentioned this in the previous video. This wouldn't be a curve that you'd be able to draw easily by hand, at least at this point. This isn't just to go to the calculator and punch it in, right? Because I don't have this equation written in explicit form. It's an implicit form. Okay, you'll see some methods for graphing curves like this in Calc 2, okay, once you get there. But let's take a look at another one. So, all right. And earlier in the section, I had given you a bunch of examples of equations that were in implicit form. Okay, so here's one of them that I had given as an example. Let's find a formula for y prime for this equation. Okay, now in this equation, it is not possible to solve for y. So the only way to find y prime, or dy dx, is to use implicit differentiation. If you don't know implicit differentiation, you can't do the problem. Let's go ahead and differentiate both sides. On the left, I'm going to have a product rule. And by the way, make sure that you identify what's a product rule, what's a quotient rule, what's a chain rule, okay? Because I'll see students just differentiate e to the y and differentiate sine x, and they get a wrong answer because they didn't use the product rule. Okay, make sure you're aware of the things that we've already gone over here in these previous sections. So I've got a product rule. I want the first, that's e to the x, times the derivative of the second. Derivative of sine x is cosine x, and then plus the second, that's sine x, times the derivative of the first. Derivative of e to the y would be itself e to the y, but since that was in terms of y, I need to make sure I tack on a dy dx, or y prime, that's the same thing. On the right, Derivative of x is 1, and then the derivative of x times y cubed, that'd be a product rule. So you got the first is x times the derivative of the second. Derivative of y cubed would be 3y squared dy dx. And then plus the second is y cubed times the derivative of the first. Derivative of x is 1. Okay, and I need to find y prime here, so I'd say anything with a y prime, let's get that onto the left. I'm going to subtract 3x y squared y prime from both sides, and then subtract e to the y cosine x from both sides. And so that's how I get this next line here. Y prime is in common to these two terms. You can factor that out. The leftover then would be e to the y sine x minus 3x y squared. Okay, you're going to divide by that expression. That way y prime is all alone. Okay, and so what you see here then would be my answer to that. Also in this chapter, we're going to have to be familiar with the derivatives for the inverse trig functions. Okay, now we know the derivatives of the trig functions. Of course, inverse trig functions are completely different, right? So y equals sine inverse of x means that sine of y equal x for values of y that are ranging between negative pi over 2 and pi over 2. Remember that when we do calculations with the inverse trig functions, we have to be aware of the range of those functions. Okay, on the algebra and trig review sheet, that last page had all the graphs of the inverse trig functions along with the domain and the range. So anyway, here's the condition on y for the sine inverse curve. Now, sine of y equal x is not in explicit form, right? This equation has not been solved for y. Here'd be the explicit form, but I'm trying to find a formula for the derivative of sine inverse of x. I'm going to have to use implicit differentiation to get that. All right, so the derivative of sine of y would be cosine y dy dx. Derivative of x is 1. Okay, and I'm solving for dy dx. Divide both sides by cosine y. Now, sine squared y plus cosine squared y would be 1. So cosine y would be the square root of 1 minus sine squared y. Now I don't need a plus minus here, since if you look at the graph of the cosine inverse curve, the y values are already positive numbers. Okay, like this graph is completely above the x-axis, so I don't need a plus minus. Now the reason why I've used that trig identity, the Pythagorean identity, is because sine of y equal x. And I'm finding dy dx, I'd like to have a formula in terms of x. Well, if sine of y is x, then sine squared of y would be x squared, right? So the derivative of sine inverse of x would be 1 divided by the square root of 1 minus x squared. This would be for values of x that are between 1 and negative 1. I'm getting that by simply stating the domain of what you see here. Okay, so of course I can't divide by 0, so x can't be 1 or negative 1, and I don't want a negative underneath the square root sign. So if you set 1 minus x squared to be greater than 0 and solve for x, that's how I'm getting this condition on x here. Now, if you were to find the derivative of cosine inverse of x, the procedure would be very similar to what you see here. Okay, you'd use implicit differentiation along with the Pythagorean identity, sine squared y plus cosine squared y equal 1. And the formula then in terms of x would be very similar to what you see here, negative 1 divided by the square root of 1 minus x squared. Here's the same conditions on x would apply then. Can't divide by 0, can't have a negative underneath the square root sign. Okay, how about y equal tangent inverse of x? Well, that means that tangent of y equals x. The conditions on the graph of the tangent inverse curve is that y is ranging between negative pi over 2 and pi over 2. Remember, that's the one with two horizontal asymptotes on it. That's the one that I've mentioned a couple of times you should know the graph of, okay? And, well, tangent of y equal x is in implicit form, so I'm going to use implicit differentiation. The derivative of tangent of y would be secant squared y dy dx. The derivative of x would be 1. Divide both sides by secant squared y, that way dy dx is all alone. And now, another Pythagorean identity that we have to know, okay, is secant squared y minus tangent squared y equals 1. So secant squared y would be 1 plus tangent squared y. I'd want to use that identity. The reason is because tangent of y is x. So I can get a formula now in terms of x. The derivative of tangent inverse of x is 1 over 1 plus x squared. Any real number is allowed for x. You're never going to get 0 in the denominator there, no matter what x is. Similarly, okay, if you were to run through the calculation for the derivative of cotangent inverse of x, it would be negative 1 divided by 1 plus x squared. Okay, how about what if we had y equals secant inverse of x? Well, that means that secant of y is equal to x, and the conditions on the graph of the secant inverse curve, if you were to check that, are such that y has to be between 0 and pi, including the endpoints. Y can't be pi over 2, though. Well, secant of y equal x, you're working with an equation that is in implicit form, so you'll use implicit differentiation. I'm doing that now. Okay, so the derivative of secant y is secant y tangent y dy dx. Derivative of x is 1. We're solving for dy dx in order to find a formula for the derivative of secant inverse of x, so divide both sides by secant y tangent y. Now secant y is x, right? How about tangent y? Well, secant squared y minus tangent squared y is 1. So tangent of y would be plus or minus the square root of secant squared y minus 1. Now, I don't need a plus minus here because if you were to look at the graphs of the tangent inverse curve and the already stated conditions on y, you would have y ranging between negative pi over 2 and pi over 2, but we already have y ranging between 0 and pi, so the overlap of those two intervals there would be y has to range between 0 and pi over 2, okay? So the y values are already going to be non-negative numbers. We don't need plus minus. Now, secant of y is x, so you're going to have, so secant squared of y would be x squared, right? 1 over x times the square root of x squared minus 1 would be the derivative of secant inverse of x. X can't be 0, okay? Of course, I don't want a negative number underneath this radical. If you were to set x squared minus 1 to be positive and then solve that inequality, you'd have x greater than 1 or x less than negative 1. Okay, now similarly, if you were to find the formula for the derivative of y equal cosecant inverse of x, it would be a similar procedure, okay? You should get negative 1 divided by x times the square root of x squared minus 1, and the conditions on x would be the same. Now, I would like you to know the formulas for the derivatives of the inverse trig functions. To me, if you know 3 of them, you know all 6 of them. Because notice how, if you know 3 of them, okay, the other 3 are just a sign change. You just put a negative in the numerator. So it shouldn't be a huge memorization thing, but these formulas will come up, okay? Be sure that you know the inverse trig derivatives. Let's take a look at some examples here to finish off the section. So how about what if we want to find the derivative of y equal x times tangent inverse of x? Well, that's going to be a product rule. right? So first is x times the derivative of the second. Derivative of tangent inverse of x is 1 over 1 plus x squared. And then plus the second, that's tangent inverse of x, times the derivative of the first. Derivative of x is 1. Here's another example. How about y equals sine inverse of the square root of x, or arc sine square root of x, that's the same thing. This would be a chain rule, right? The square root of x is inside of the sine inverse function. So I'm going to begin the problem as if I were just differentiating sine inverse of x. Here's the formula. 1 divided by the square root of 1 minus x squared. Now I don't have sine x, I got sine inverse of x, I've got sine inverse of the square root of x. So basically where I see x in this formula, I'm going to replace that with the square root of x, but then I got to finish the chain rule, right? I got to multiply by the derivative of that thing that I was ignoring. The derivative of x to the 1/2 would be 1/2 x to the negative 1/2, or 1 over 2 x to the 1/2, or 1 over 2 x to 2 times the square root of x, okay, if you're using radical notation. Simplify that. Square root of x squared, that'd be x. Okay, and you can get a single radical there with those two terms. And again, simplify as far as you can go with all this stuff here. Here's another chain rule. Okay, e to the 2x is inside of the secant inverse curve function. Okay, so I want to differentiate. This is actually going to be a chain rule within a chain rule. Well, here's the derivative for secant inverse of x. So I don't have secant inverse of x, right? But I'm going to start with this formula, and where I see x, I'm just going to replace that with e to the 2x. And so I've done that. But now I got to take the derivative of e to the 2x, because I got to finish the chain rule. The derivative of e to a power is e to the power times the derivative of the power. So I'm going to say e to the 2x, and then times the derivative of 2x would be the second time that I'm using the chain rule, that'd be 2. E to the 2x will cancel with the 1 here, leaving you with 2 divided by e to the 2x squared, that'd be e to the 4x. Okay, and so here'd be my answer in a simplified form. All right, that's it for this section. So be sure that you look over the homework problems that are on page 215 for me, the odd numbered problems listed there.